All right, guys. So in this section, we are going to be talking about an intro to logarithmic functions. We are going to be using a graphing calculator as well. Pretty much everything I show you today can be done with the Desmos scientific calculator, but I also wanted to show you some features of your TI graphing calculator that some of you might find useful. It should be worth noting that these features are only going to be available on certain calculators. They will not be available on TI-83 graphing calculators, and even some of the TI-84 calculators may not have some of the features that I show you today. And if they don't have the feature, you'll just have to do it the other way that I show you using what's called a change of base formula. So to begin with, let's talk about what a logarithmic function looks like. So I've got that written in the box here for us, where it says f of x is equal to log base b of x. If you're wondering how to read that, I've got that to the side in quotation marks for you. So you read it as log base b, so fill in with the blank there, log base 2, log base 10, so on, of, and then whatever is inside the parentheses of x. If there's not parentheses, then that's just going to be whatever number or whatever variable comes after the log. Now that number or variable that goes after the log and oftentimes gets put in parentheses is what is known as the argument for the logarithm. Now, a couple of other quick facts about logarithms. Logarithms are the answer to the question, what power? What power do we need to raise a number to for it to be equal to a given value? It's our way of kind of undoing exponential functions. We already knew that, so it should make sense that they answer the question, what exponent or what power would we need? Now, most calculators are only going to be able to do logarithms if the base is either 10 or the special base that we talked a little bit about in last unit, which is the base e. Let's start by talking about the base of 10. When you have a calculator that does a log with base 10, we typically call that the common logarithm. So in other words, what we've got right here written, log base 10, is what is known as the common logarithm. And it's assumed that if the base is not written there, so log of x, log of x, we assume that the base is a 10. So notice that log base 10 can also be written as log of x. It'd be similar to saying that if you're taking a square root, we really don't need the index of 2 right here. We can just draw our square root symbol. Or, if we have x to the first power, we can just write that as x. Same idea here. If we have log base 10 of x, we can just write that as log of x. Okay, so let's just do some practice with typing these into a calculator. In fact, the first two are probably ones that you wouldn't need to use a calculator for, but we'll still show how to do it anyways. So the first one, log of 100, which remember would be the same as saying log base 10 of 100. And what that's asking is 10 to what power is 100? And you could probably already think about what that number is going to be. 10 to the power of 2 is equal to 100. So log of 100 should be the number 2. Let's see if it is. So the log button on your graphing calculator is going to be to the left of the 7 key. On Desmos, you can just type log, or you can find the button there as well. So let's take the log of 100, and then we will close our parentheses and press enter. And it will, in fact, tell us that the log of 100 is equal to 2. So in the same way, on number 2, you could probably do this without a calculator. Log of 10, you're asking yourself 10 to what power is 10? And obviously 10 to the first power is 10. Let's now check that with our graphing calculator. If we take the log of 10, it does in fact give us the number 1. Now for this third question, log base 10 of 25, we're not going to really probably know what that is just in our head. 10 to what power is 25? Well, it's not going to be a whole number. It's going to be some kind of a decimal. And so that's where the calculator is going to become pretty useful. And so to type this into the calculator, remember log base 10 is really just taking log of 25. So don't worry about the 10 being there. All you need to do in your calculator is to type in the log of 25 and close your parentheses, and that will tell you that the answer is 1.39, and let's just go to, let's go 3 decimal places, 1.398. Now, what that's saying is that if you take 10 to the power of 1.398, that should be about 25. In fact, I should probably be a little bit more careful when I write this. Instead of saying equals 1.398, this really should say is approximately 1.398. And that'll become especially important when we get to solving later on in this unit. And if you wanted to check that, take 10 to the power of that number that you just found, so 10 to the power of 1.3979 and so on. And when you press enter, it should give you a number very close to 25. In this case, 25.00000 and a whole bunch of zeros. It looks like it has a 2 at the end of it, most likely just due to some rounding that we had to do in order to get that number to fit on the calculator. Alright, so obviously calculator can be very useful when you're finding logs with base of 10. But what happens if the log is a base of something other than 10? Well, we've got two options. The first is if we just need to maybe answer a quick multiple choice question or something like that, you might just estimate the logarithm. In fact, that's a really good skill to use, especially when taking like an ACT or SAT if you don't have a calculator available to you, or if you don't have time to type it into your calculator. You can just estimate it, and you can usually get pretty close. So the second option then is going to be change of base formula. So that'll be a formula that you'll have to remember in order to find the exact value for the logarithm. And again, some calculators will actually be able to handle bases which are not 10, and if that's your calculator, I'll show you how to use that feature, but you should still know change of base formula. Alright, so when we estimate the logs, let's kind of talk about how this works. So in the first one, log base 10 of 55. Now, it does have a base of 10, so yeah, we could just type this into our calculator, but let's just practice estimating. So this is asking 10 to what power is 55, and I don't know what that's going to be. But I do know that 10 to the first power is 10, and I know that 10 to the second power is 100. So when I want to know what is 10 to what power is 55, I know that that's going to have to fit somewhere in between 1 and 2. In other words, our estimate for, I'll just call it x, is going to be somewhere probably between 1 and 2, and let's just think about it maybe being halfway. Let's go out to maybe 1 decimal and say that maybe x is maybe about 1.5. Now we'll actually be able to check that. What is log of 55? And it turns out that the log of 55 is 1.7. So we were off by a little bit, but 1.5 is fairly close. And I'll just go ahead and write that down for this one since we had the actual value. So yeah, 1.7 is the exact value, or the closer approximation. 1.5 is just our estimate. For the next one, we're going to do the same thing, but this time using 750. So now thinking about powers of 10, we've got 10 to the first power, which is still 10. We've got 10 to the second power, which is 100, and 10 to the third power, which is 1,000. And the reason why I went out to that power is we're wondering what power would we need to take 10 to in order to get 750, which actually fits in between those two values. So in the first case, it fit between 10 and 100, so we knew that our exponent had to be somewhere between 1 and a 2. This time 750 fits between 100 and 1,000, so we know our variable is going to have to be, or our exponent is going to have to be somewhere between 2 and 3. Now 750 is a lot closer to 1,000, so I'm going to say it's probably a lot closer to 3, maybe like something 2.8 or 2.9, something like that. And then let's go ahead and check and see how close we were. So 10 log base 10 of 750 is equal to 2.87, so actually a little bit closer to 2.9, and so we got a little bit more accurate with our approximation and with our estimate on that second problem. Now in number 3, we finally see a base that's not 10. We see log base 2 of 12. And so what we need to do is we need to ask ourselves 2 to what power is 12? And well, let's see, 2 to the first power would be 2, 2 to the second power is 4, so it's not going to be in between those. We've got 2 to the third power, which is 8, and then 2 to the fourth power, which is 16. So if we want to know 2 to what power is 12, well, 12 fits in between 8 and 16. So our exponent would have to be somewhere between 3 and 4. Let's just say maybe closer to 3 point, maybe 6, and let's see how close we are. Well, here's the problem. We don't have that in our calculator just yet. We'll be able to check it in just a little bit, though, with change of base formula. So hold on to that, and we'll see how close that approximation is. Next, for log base 2 of 40, obviously 40 is more than our powers of 2, so let's just keep going with some more. 2 to the 5th power is 32. 2 to the 6th power is 64. And if we want to know 2 to what power is 40, then that's going to have to fit somewhere in between 32 and 64. So our exponent is going to have to fit somewhere between 5 and 6. Since 40 is closer to 32, it's probably going to be closer to 2 to the 5th power. Let's say the exponent is maybe about 5.2 maybe, and then we'll check later on to see how close we were. So remember, estimates, they're not exact. They're just there to give you a rough idea of kind of where the value is. Can be useful when all you need is either an approximation or maybe you are answering a multiple choice question, and by estimating, you can eliminate some of the other choices to get you closer to the value that you would want. But sometimes we need the exact value, and estimating is not going to just cut it. Well, that's where this change of base formula can actually be very nice. So let's say you were trying to find log base b of a. It actually turns out that you can find that by taking the log of a divided by the log of b. And when I write those, I mean that you're taking the common log. In other words, log base 10 of a over log base 10 of b. And what that allows you to do is this formula allows you to, using log base 10 or the common log, find logarithms that aren't actually would have been available to you otherwise. So let's use that actually to check our answers for numbers 3 and 4. What that formula says is that log base 2 of 12 can be found by taking the log of 12 divided by the log of 2. So let's type that into our calculator. If we type in log of 12, make sure to close your parentheses before hitting divide, and then typing in log of 2. Then 3.58, which is 3.6, is what the approximation would be. And hey, look at that. We got pretty darn close. You know, even with rounding to the nearest tenth, we were spot on. We could do the same thing with number 4, log base 2 of 40. We could find by taking log of 40 and dividing by log of 2. And so that would be typing in log of 40 divided by log of 2. And let's see how close that estimate was. 5.3. And we had 5.2. So again, pretty darn close to what you would have expected based on our estimate. So you can see estimates can actually get you pretty close and are a pretty quick way to come up with some good approximations. But change of base is nice because it does give you the exact value. So let's do a couple more examples of using this change of base formula. So in the next example, we've got log base 5 of 10. Using change of base formula, we can rewrite that as log of 10 over log of 5. So notice that the base always goes on the bottom of the fraction. So if you need a quick way to remember that, that would be an easy way to do so. And if we take log of 10 divided by log of 5, that's going to be 1.43. Notice that it did ask us to round to the nearest hundredth for each of these problems. So we'll make sure and round to the correct place. So 1.43 as a decimal. Next, for number 2, log base 3 of 18. We'll take log of 18 divided by log of 3. So log of 18 divided by log of 3. And that's going to be equal to 1.58 when we round to the nearest 100th. Again, make sure you're using that approximation sign when you are writing your final answer. I need to go back and fix that for number 1. I'll need to make sure and do that as well. Okay. For the next one, on number 3, we're looking for log base 2 of 8. So we can find that by taking log of 8 divided by log of 2. So let's see what that gives us. If we have log of 8 divided by log of 2. That gives us the number 3. And that was a whole number. So actually, we don't need the approximation symbol this time. We can say that it's exactly 3. And if you think about why that is, think about what the log is asking. 2 to what power is 8? Well, we actually probably could have just done that without the calculator because 2 to the power of 3 clearly is 8. So we could probably use that on number 4 as well. 4 plus log of 100. Remember that this is log base 10. 10 to what power is 100? That's just the number 2. And 4 plus 2 is 6. Or if you weren't sure, just type it into your calculator. For the last one, 5 minus log base 2 of 7. Here we're going to have to probably use calculator because 2 to what power is 7 is not going to be a whole number. So that's going to be 5 minus, and then use your change of base formula. So 5 minus log of 7 divided by log of 2. And so what that's going to be is it's going to be approximately 2.19 when we round that to the nearest hundredths place. Now, I mentioned that there was actually a button that will allow you to use different bases on certain calculators. That button is found under the Math option. So if you go to Math and then go up from the top of the menu, option letter A will say log base, and that will actually allow you to type in things like log base 2 of 7 without having to use change of base formula. And then obviously if you were going to do that, you would just take 5 minus log base 2 of 7 written this way, and you'll get the exact same answer that we did before. Now I mentioned that feature only because it might be useful to some of you. It's not going to be available on every calculator, so for those that don't have that option, you'll definitely need to remember change of base formula when working through each of those problems. All right. Now the second part of the notes for Intro to Logarithms are going to focus on this new irrational number that we had started to talk about, which is the number e. E is what's known as Euler's number. It was discovered by Leonhard Euler, who was a Swiss mathematician and a physicist who was alive in the 1700s. Now the decimal for E is approximately 2.71828, and then it does continue on forever, similar to pi. When E is used as the base of a logarithm, we call it the natural logarithm. It is written as ln of x. In other words, instead of the common log where we had log base 10 of x was log of x, log base e of x is written as ln of x, or natural log of x. Now, as far as the inverse property goes, remember that natural log and e are inverses of one another. In other words, if you are taking the natural log of e to the power of x, natural log and e will cancel, and that will just be x. In the same way, if you take e to the power of natural log of x, or any number, again, both natural log and e will cancel, and you just get x left over. So that can be kind of nice, because it definitely can save you some time on certain types of problems. So let's go ahead and just do some practice with going ahead and typing in each of these different values. So the E button on the graphing calculator is going to be right above the ln button, so ln for natural log. So you'll hit second, and then that ln button to get E. And in this case, for number 1, we just want e to the power of 3. Let's just go ahead and go to 2 decimal places, so that would be 20.09. Next, we want to take e to the power of the square root of 5. So again, we'll hit e. And then for square root, second x squared, power of 5, enter. And that's going to be about 9.34. If you're using the Desmos Scientific Calculator, you should just be able to type in the letter E on your keyboard, and it will know that you mean the number E. For the next problem, we want to find 2 multiplied by e to the power of 0.1. So again, just type that into your calculator to get an approximation, and that's going to be 2.21. Next, we want to find the natural log of 1. And so the natural log of 1, instead of hitting second and then natural log to get e, we can just hit ln and then type in the number 1, and that will tell you that the natural log of 1 is 0. Next, we want to find the natural log of 0.9. So again, hit that natural log button, type in your number 0.9, and we actually get a negative value. So negative 0.105, so I guess 0.11 if we go out to two decimal places. So it's possible that when you take the natural log of a number that you get a negative answer. Well, what happens if we try to take the natural log of a negative number? So the natural log of like negative 2.5. Well, now we're going to run into a problem. In fact, if it gives you a number, it's going to give you a number with I attached to it. And that's going to be because it's a complex number. Otherwise, what you will most likely see if your number is not in complex numbers mode, if it's just in real mode, then when you try to type in the natural log of negative 2.5, you're going to get an error message. And it's going to tell you that it's a non-real answer, which we already kind of know because based on our last time we typed it in, where it was in complex mode, we did get a complex number, which is not a real number. And so, in this case, what we're going to write is not error, we're going to write that it's undefined. And the reason for that, remember the base of the logarithm is e. So you're asking yourself, e to what power is negative 2.5? Well, remember e is a positive number. And if it's a positive number, then it can't all of a sudden become negative. It's not as if you can multiply a positive number a certain number of times and all of a sudden it changed to be negative. And so your natural log arguments cannot be negative. So the argument, I'm going to write this down for you. So the argument for a natural log cannot be negative. In fact, that's usually the case for common logs as well. If we tried to find the common log of negative 5, we would get a similar answer. So the argument will always need to be a positive number. All right, for numbers 7 and 8, you could go ahead and put these into a calculator, but it's probably easiest to just use the inverse property of logarithms that we talked about in this box right here. To know that if you have e in natural log, they will cancel with one another, and the answer to that is just going to be 2. And similarly, on number 8, natural log and e will cancel. That'll leave you with just the number 8. Using that inverse property, we can actually convert from one logarithm form to another, or from one form of an equation to another. So if we had something like e to the power of x equals y, then the opposite of taking e to some power is to then use the natural log. So if we were to take the natural log of both sides of our equation, the natural log of e to the power of x is equal to the natural log of y, we'd be able to cancel out the natural log in e and know that x is equal to the natural log of y. That's what's known as the inverse property of logarithms, and that's how you can use it to convert from exponential to logarithmic form. So let's do a couple problems practicing that. Starting with number 1, if we have e to the power of x equals 20, then what we can do is we can take the natural log of both sides of our equation. In doing so, we can cancel out natural log and e to find out that x is equal to natural log of 20. And then if you were solving, you could go ahead and type that into your calculator to get a decimal approximation. We were only asked to convert between one form and the other, so we'll just leave that as our final answer. Similarly, on number 2, if we were to take the natural log of both sides of our equation, natural log of e to the 5th is approximately natural log of 148.41, we would be able to then cancel out natural log and e to get that 5 is approximately the natural log of 148.41. Again, once you get to that point, you've converted from exponential to logarithmic form, you're done. But just out of curiosity, I'm always curious to see, is that actually true? If I take the natural log of 148.41, is that about equal to number 5? And I would say yes, pretty darn close. 4.9999 on 78714 is ridiculously close to 5. So I would say, yeah, that's a pretty good approximation. Now, when we get to number 3, notice that number 3 already has natural log in there. So you probably don't want to try to take the natural log because now you just have the natural log of the natural log of x, and that can be kind of confusing. Instead, what we're going to do, the opposite of natural log is to take e to some power. So instead, let's take e to the power of both sides of our equation. So e to the power of natural log of x, and set that equal to e to the power of 5. That way, e and natural log will be there to cancel, and we'll get that x is equal to e to the 5th power. Again, we could then type that into a calculator to see what the decimal approximation is, but since all we were asked to do is convert from one form to the other, we can be done at that point. So number 4, using a similar strategy, let's take e to the power of both sides of our equation. So e to the power of natural log of 4 is approximately e to the power of 1.39, and that way e and natural log can cancel, and we'll have that 4 is approximately e to the power of 1.39. Again, we've already converted, so we are done at that point, but I'm again just kind of curious, what is e to the power of 1.39? So if we take e to the power of 1.39, is that about the number 4? And yeah, pretty close. Not quite as close as it was on number 2, but 4.01 is still pretty close to the number 4. All right, guys, that is all I've got for us in this section. One thing I would suggest that you do, though, is using your MacBook when you've got some free time, try to find at least one real-world application for our irrational number e, or try to find an interesting fact about Leonard Euler. Either one of those would be some interesting stuff for you to kind of look up. In fact, there's a possibility that I might ask you a question on the quiz this week to see what interesting fact or real-world application you found while you were doing the notes today. So make sure you do that in case I ask that question on the quiz on Friday. Until then, have a good rest of your day.